All right. In this video lesson, we're going to look at calculating percent composition. This video should be putting into your notes some information that maybe you already know about percent composition. So, you may have watched some other videos, or we may have talked about this in class already. But the goal here is to get the process of calculating percent composition into your notes. Okay, so you will have some check-ins on calculating percent composition, and we will use it more in our course as we continue going through. Okay. So the reason we care about percent composition is that what can happen is if we produce a new substance, even if we don't know the formula, what we can do is determine its composition by mass, and then we can convert the mass amounts to percentages to give us percent composition of a substance in this new or the percent composition of the substance. So we can figure out how much of everything is in a new substance. So this is common in pharmaceutical companies when they develop new medications. And in plastics, etc. So percent composition is basically what it sounds like. It's how much an atom contributes to the overall mass of a compound. So what we do is we figure out how much by mass each element contributes to the overall mass of the compound. And we calculate it exactly the same way that we would calculate percent for anything else. So we're just going to dive right into an example. In our example here, we have found that an experiment has revealed that 2.5 grams of hydrogen reacted with oxygen to produce 22.5 grams of water. So we want to know what the percent composition is of water. Now, just a reminder that you're going to need to hit pause and copy the information that you see in this lesson. So I would hit pause and get this copied now. Okay, so what we need to do first is, in order to calculate percent composition, we have to have mass information for all of the elements and the compound as a whole. So the first step we have to do for this example is figure out the mass of everything involved. So that means we need a mass of hydrogen, a mass of oxygen, and a mass of water. Now, up in the given information, we can see that we have the mass of hydrogen at 2.5 grams, highlighted in blue, and we have the mass of water at 22.5 grams, highlighted in yellow. So those are very easy pieces of given information. We don't have the mass of the oxygen, but you should remember that the mass of the reactants has to equal the mass of the products. So we can calculate, if we look here, we can calculate at the bottom of my screen the mass of oxygen, because it's going to be the mass of the water subtract the mass of the hydrogen. So we write out our formula, we sub in our numbers, and we find that the mass of oxygen is 20.0 grams. So that's the first step. We need mass information for everything involved. The second step is we're going to calculate the percent composition by mass. So we start like this. I've already started, and I've written the percent of hydrogen is going to equal, this is pretty straightforward. We go mass superscript hydrogen divided by mass superscript water times 100%. So because we're going to communicate this properly, we're always going to write our formula, and then we're going to sub in our numbers. We have a mass of hydrogen has been determined, or is in the givens, and it's 2.5 grams. And our mass of water was in the givens at 22.5 grams. And then we finish off with the rest of our formula times 100%. So we punch this into our calculator, we do the math, and we get 11.1%. And you're checking your significant digits. Okay. And then we're going to do exactly the same thing for oxygen. But this time our formula is mass of oxygen divided by the mass of the water. And you have to put the oxygen and water in subscripts. And we're going to times it by 100%. So this is just the formula for percent. So you take what you have divided by total amount. So we're going to go equals. Subbing in our value, we calculated the mass of oxygen to be 20.0 grams. We already know the mass of the water. It was in the givens, and it was 22.5 grams. And we're going to go times 100%. And we punch this into our calculator, and we get 88.9%. Okay. So because this is a percent composition and percent is out of 100, we know that the percents should add up to 100. So at this point, you should do a quick check and see if your numbers add up to 100. Because if they don't, you've made a mistake in your calculations. The other thing I want you to notice is that I have included my units after every single number. That is proper communication. So if you want good communication, you have to do that. After we calculate our percents, all we do is finish off with a therefore. So we go, therefore, percent composition of water is 11.1% hydrogen and 88.9% oxygen. All right, so if you haven't, hit pause. Make sure you've got this copied down. And now we're going to look at another example. So in this example, experiment number 2, we have an experiment. There is 3.45 grams of sodium reacted with 5.33 grams of chlorine to give 8.78 grams of NaCl. Now we want to know what the percent composition by mass of sodium chloride is. So whenever I'm doing problems, I always like to write out my givens. So I've started and I've written out my given information. Sometimes, if you're struggling to think about how to start, writing out your givens might give you a clue. So I always start by writing my givens out. I pull all the numbers from the written word problem and I write them on the left. And now I'm going to figure out my percent of sodium and my percent composition of chlorine. So if you want, hit pause and try this yourself. And then when you're done, hit unpause and check your work. Okay, so if you follow this process, you write out your formula like you see right here. You sub in your numbers and then you get an answer. That is proper scientific communication. So you want to make sure that you are showing me all of this work. If you have calculated it correctly, you should have 39.3% sodium and 60.7% chlorine, and you're finishing off with a lovely therefore statement. So the last 2 problems that we've solved are using experimental data. Because it's using actual masses in grams, it's called experimental percent composition. The mass values comes from experimental data, and the mass is measured in grams. So hit pause, make sure you've gotten this all copied. Now, if we happen to know the molecular formula of a substance, we can calculate percent composition a different way. And this way is called a theoretical percent composition. If we have the percent or the molecular formula, we can use atomic masses for each element and the molecular mass of a compound to calculate the percent composition. When we do this, like I said, it's called theoretical percent composition, and we get the mass values from the periodic table, and they have the units atomic mass unit. The process is exactly the same. We use exactly the same formula. Make sure you have this copied. And we're going to do an example. And I'm just going to show you the example instead of doing it with you because it's very, very straightforward. So in our example, all it's going to do is ask you to calculate the percent composition for a compound and give you the formula. So like right here, I have carbon dioxide. So instead of having mass values in grams, we have to use our periodic table. We're going to go to our periodic table and we're going to get our atomic mass of carbon, and we see that it's 12.01 atomic mass units. We get our mass of oxygen, it's 16.0 atomic mass units. So those are the two elements involved. Because carbon dioxide has two oxygen atoms, you see highlighted in red, that means we have to multiply the atomic mass of oxygen by 2 because there's two oxygen atoms contributing to the mass. That means that the mass of oxygen involved is 32.00 AMU. Then we just have to calculate our molecular mass like we've already learned how to do for carbon dioxide. We have 12.01 atomic mass units plus 2 times 16.00 atomic mass units. We end up with the theoretical mass of carbon dioxide is 44.01 AMU. That's the only difference between theoretical percent composition and calculating experimental percent composition. It's just where the mass data is coming from. We use exactly the same formula. So we are still using mass of, for percent oxygen, we're still using mass of oxygen over mass of the overall compound, CO2, times 100%. We're still subbing in our data and solving. And then exactly the same thing for carbon. We're getting our mass of carbon divided by our mass of carbon dioxide times 100%. Sub in our numbers, get our percent, and we finish with a therefore statement. So the big learning, actually make sure you have this copied. So the biggest pieces of learning for this is just taking a concept you already know how to do, so calculating percent, and applying it to compounds in chemistry. Experimental percent composition is when we get our data from experimental mass values in grams. Theoretical percent composition is when we get the mass values from the periodic table. Okay, so that is it for percent composition. You will have some practice to do, and you will have a check-in coming your way at some point in the near future. So make sure you that you do some of the percent composition practice. Remember, if you have multiple of one atom, like in our carbon dioxide, you multiply that by 2 to get the overall mass of the element. Okay, that's it, folks.